This video is about arc length parameterizations and arc length parameters. To motivate this video, I want to make the following observation, which is that parameterizations for vector valued functions are not unique. That in general, we can have two different vector value functions that both trace out the same curve. So for example, we could have R1 of t be cosine t, sine t and 0, where t runs between 0 and 2 pi. Where we could have R2 of t to be cosine of t squared, sine of t squared and 0, where t runs between 0 and square root of 2 pi. Now, the thing here is, okay, let's take a look at these two. These two trace out exactly the same curve. That both of these, in fact, are just going to trace out a unit circle in the xy plane. But, as t goes from 0 to pi, t squared, or sorry, I guess I should say, as t runs from 0 to square root 2 pi, t squared runs from 0 to 2 pi. These both trace out a unit circle. So the question we want to ask is, which one is nice? Or equivalently, what properties should a good parameterization have? And so if you trace out these two parameterizations, if you do R1 of t as cosine t sine of t is 0, you just go around nice and constantly like this. Nice constant speed. Whereas for R2 of t, it starts off slow, but then as t gets bigger and bigger, it goes faster and faster. So it starts off slow, and as t gets bigger and bigger, it goes faster and faster around. So it's moving faster over here than it is here, and we're thinking of this as a particle moving around the circle. Is what's being described by R2 of t. And so we should probably think based off of that kind of gives some hint that R1 of t is nicer, is better than R2 of t. It's not just that, the formula looks simpler, this looks simpler than this, but, having this idea of constant speed gives us a way to make that precise. So, if our parameterization is like this, I'm just moving at constant speed here, this would be a lot better parameterization than, slow, 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 fast, 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 slow, 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 fast, 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 fast. Constant speed is good. So after all of that ado, here's our definition. If r prime of t, if the magnitude of that is equal to 1 for all t, r of t is what we call arc length parameterization. And so this is saying the speed, the magnitude of v of t equals 1 is constant. The speed is constant and the speed is equal to 1. So going back to this example here, if we do calculate out things for R1 of t and R2 of t, R1 prime of t is going to be negative sine t cosine t 0. R2 prime of t is going to be, okay, so now we have to use a little bit of the chain rule here. So it's going to be negative 2t sine of t squared, comma, 2t cosine of t squared, comma, 0. And if we take their magnitudes, the magnitude of R1 prime of t, the speed of this one, is the square root of negative sine t squared plus cosine t squared. is sine, this is sine squared t, this is cosine squared, add them together. We get 1. Great. This is an arc length parametrization. But if you try to do the same thing for R2 prime of t, you would get the square root of negative 2t sine of t squared squared plus 2t cosine of t squared squared. And this ends up as, let me go to this slide here. The rest of the calculations here are 4t squared sine squared of t squared plus 4t squared cosine squared of t squared. And so if you crunch this one out, assuming t is positive, which we can do here, this ends up as 2t. So this of course is the speed of R2 of t is 2t, and this shows here as t gets bigger and bigger, the speed here gets larger and larger. Okay, so that is the motivation for what's going on here. And so then in order to get to an arc length parameterization, so now we're thinking about how do we get to an arc length parameterization. The book makes this definition here of an arc length parameter. S of t, S is our arc length parameter. It's defined to be the integral from t naught to t of, you can do the magnitude r prime of t dt, but of course that's just equivalent. These are just equivalent. R prime of t is v of t. You're integrating the speed from t naught to t. And the idea here is that this is the distance traveled from time t naught to time t. So you're starting at time t naught, and this is the total distance traveled from that initial starting point to time t up here. And there's one little thing I need to do here. This is poor notation because I'm using t in 2 different ways here. T up here, and the t here is different from that t here. So maybe we will call that t1, because we want to separate out that this t as one of the bounds of our integral is different than the variable we're integrating with respect to. So given this definition here, and given this goal here, we're now going to talk about how to find arc length parameterization. So the point here is I give you some r of t. I give you some r of t here, and let me edit all of those there. I give you some r of t, and you want to turn it into an arc length parameterization. So how do you do that? You compute r prime of t. So that's the velocity, this is the speed, and then you compute the arc length parameter from the previous slide. And so then you have s written as a function of t, and then you're going to invert the formula. So s is a function of t, you're going to write t as a function of s. You're going to use your answer, substitute it into your original parameterization, your original vector value function, and then it's a good idea to check at the end to make sure you do in fact have an arc length parameterization. So as an example here, let's find arc length parameterization for this one right here. This should look familiar. This is our helix example that we return so often to. So the very first thing we have to do is we need to compute r prime of t is going to be, take the derivatives here, negative sine t I hat plus cosine t j hat plus 1 k hat. And then we need the speed. So this is going to be a square root of negative sine t squared plus cosine t squared plus 1 squared. Sine squared t plus cosine squared t is 1. 1 plus 1 is 2. So this is the square root of 2. So then at this point, our arc length parameter, so s of t, is the integral from t naught to t of square root 2 dt1. Okay, so, and if you don't like using t1 here, we have too many different t's. The textbook, I think, uses a tau. And that's the lowercase Greek tau. Tau is the Greek letter that corresponds to t. Okay, so this is what's going on here. Let's also do this with what is t naught here. Let's make the decision to set t naught equal to 0. We make the decision to set t naught equal to 0. This is now the integral from 0 to t, the square root 2 d tau. And this is should be a straightforward enough integral to evaluate. This is just square root 2 times t. Okay, so where are we in our list of things to do here? We computed r prime of t, we computed the velocity, the speed, and we computed s, the arc length parameter formula right here. So step 2 is we need to solve for t in terms of s. So right now we have s is equal to square root 2 t. Solving for t in terms of s is merely divided by square root 2. So t is equal to s divided by square root 2. So then part 3 here, substitute into r of t. So everywhere you see a t up in here, we're going to replace t with s divided by square root 2. So r of t is, going to now be r of s divided by square root 2. And so this is going to be cosine, let me just kind of leave this here, cosine of s divided by square root 2 I hat plus sine of s divided by square root 2 j hat plus s divided by square root 2 k hat. So now I just get rid of the s divided by square root 2. I can just write here, let's say r1 of s is just cosine s divided by square root 2 I hat plus sine of s divided by square root 2 j hat plus s divided by square root 2 k hat. This is an arc length parameterization. Out. Maybe I should be drawing some mountains here. I have nice snow-capped mountains. Okay, so the thing that I'm asserting here is that this traces out exactly the same curve as this does, but it does so at a constant speed. The speed is 1. So the very last thing I wrote here is let's check that. And so r1 prime of s is going to be, so take the derivative here, negative 1 over square root 2 sine of s over square root 2 I hat plus 1 over square root 2 cosine of s over square root 2 j hat plus 1 over square root 2 k hat. Take the magnitude of this, and you end up with negative 1 over square root 2 sine of s over square root 2, all of that squared, plus 1 over square root 2 cosine of s over square root 2, all of that squared, plus 1 over square root 2 quantity squared. And so what is under our square root? We have, this will be 1/2 sine squared s over square root 2 plus 1/2 cosine squared s over square root 2 plus 1/2. And this ends up as 1/2. So these are just, you know, sine squared of s over square root 2 plus cosine squared s over 2 is just 1. So these terms add together be 1/2 plus that 1/2 over there. We have 1 as desired. Okay, so a little bit of lengthy video. I wanted to say one last thing, which is in general, computing arc length parameterizations is a difficult thing. This is, you know, oftentimes we just have to leave things unevaluated here because these integrals can be very, very difficult to evaluate. In order for me to have an example that you can compute an arc length parameterization for, it has to be a kind of special case like this.